Hello, my name is Josiah Deleon, and this is my submission to the Senior Project Symposium. The faculty member overseeing my project is Professor Mohamed Ali. Professor Ali has allowed me to submit a project I am working on with my company, and in turn, the company I am working for, Thomas Global Systems, has sponsored the project. The title of this project is Active and Lightweight UAV Camouflage. Here's the abstract of my project. Now I won't bore you by sitting here reading it in monotone, so let's continue on to the next slide. However, if you would like to read the abstract, feel free to pause the video. The main idea behind this project is simple. The military still uses low-flying drones for reconnaissance. Now these aren't the big drones you see in the movies or the drones that you imagine the military uses. These are the ones that you can control with an RC remote. These drones fly at a low altitude and are easy to spot by a ground observer, and this is where our project comes in. We're trying to create a system that is able to reduce the signature of these types of fixed-wing UAVs. The package must be lightweight environmentally and electronically. This package cannot affect the drone's flight time, whether that be through the weight of the package or the amount of power that the package consumes. This is a simple system. It doesn't require too many electronics and the weight is kept to a minimum. The design of the system takes an average color, in this case it would be the average color of what is above the UAV, and dynamically reproduces it on the bottom side of the UAV. The challenges involved with this are, how do we get the color? How much of the sky does this have to emulate? How do we reproduce this color? How do we make sure this does not reduce the flight time or payload capacity of the UAV? Here's the block diagram for the system that I came up with. Each one of these parts will be explained more in depth in the coming slides. This is the basic overall system for the package. The optic is one of the most important parts of the system. This is how the color that we are trying to reproduce is generated for the system. A spherical optic was chosen due to its shapes and its properties. The optic captures a wide field of view, and the light within the optic is then scattered within. The scattering of light allows for an averaging of the color. As you can see right now, the optic is not much bigger than a pencil. For future designs, we may keep it small due to its weight, or we may go larger if needed. As now the optic itself can perform quite well for its size, and we are still able to get the averaging effect of the light above it that we want. The electronics of the system are the next part. A sensor can read this average color from the optic and then transmit this color over a data bus into the microprocessor. An algorithm was created to convert the received data. This converted data is then sent to the next part of the system. I created the PCB shown to incorporate the microprocessor and the bus wires into a smaller area. This PCB is not finalized, as this project is in continuous development and the design of the PCB will change with the demand. Even though we may plan to increase the complexity of the electronics, we plan to keep the area of the electronics the same size. The brains from the previous stage manipulate LEDs in order to reproduce the color that is received from the optic. The light source then injects this light into a very thin light guide. This light guide has a pattern on it that evenly distributes the light throughout the entire light guide. This creates the effect that the whole plane is evenly illuminated and one side isn't dimmer than the other side. This pattern is put onto the light guide through etching or laser cutting, and the pattern itself was generated from an algorithm created by Thomas Global Systems. The light guide plane is extremely thin, less than 1 millimeter, and this is what goes onto the bottom of our UAV. Now, unfortunately, we don't have the correct tools to properly create this pattern on one of our light guide planes, so the results weren't what we wanted. We plan to get the right tools later down the line. For proof of concept purposes, we use different techniques to get the light from our light guide plane. This project is a proof of concept demonstrator for Thomas Global Systems, along with being my senior design project. In the small scope, color reproduction and distribution were achieved. The light guide plane still needs to be worked on, and when we get the tools to properly create the pattern onto a light guide plane, it will look much better. We are planning on doing most of that in the past month. However, due to events happening in the world right now, most of us are required to stay at home. This project is being worked on with Thomas Global Systems, and a lot of that work requires me to be in the lab. Therefore, many of the milestones we planned to meet this past month have been postponed. In conclusion, it seems possible to apply the system to a reconnaissance UAV in order to reduce its signature to ground viewers. The final design will only contain a few sensors for redundancy purposes. We do not plan to use cameras or image processing. Our system will be simple in code, therefore it'll reduce the chance that a failure may occur due to software. We have also sourced a brighter light source for our light guide, along with continually researching and looking for thinner materials to use as our light guide. We plan to keep our system's power lower than 30 watts, and as of now, it consumes about 12 watts of power. This project is still ongoing and is in continued development with Thomas Global Systems. In these next slides, I will show you the progress of the project and how it has continued to change throughout my senior year. In this first slide, it is the first test of the color detection system. On the left-hand picture, I am shining a white light directly at the color detection system. It looked more red in the photo, however in person it was much more white. In the right-hand photo, I am shining a light through a blue sticky note, and we can see that the light guide panel I was using changed to blue. Now this proves that the color detection system was working for the time, however, it was much improved on later. This is the first mobile prototype of the system. Now the system is large and bulky, however, we mobilized it. In each one of these photos, I am holding a different color above the optic, and that optic is transmitting that data into our microprocessor. The microprocessor is then converting that color into our light guide plane. Our light guide planes are not different colors, however, the color of the light guide plane is being manipulated by the system itself. In the first photo, I am holding a blue bag above the optic, and we can see that the blue is being reproduced on this light guide. On the second photo, I am holding a red piece of tape, or I think it was a red roll of tape, above the optic, and that red color is being reproduced on the light guide. And in the third photo, I'm holding an orange sticky note above the optic, and that orange is being reproduced on the light guide. This slide is showing the second mobile prototype we produced. As seen in the picture to the right, this prototype is much smaller than the first prototype while being able to drive a much larger panel. The new prototype also weighs about 1/4 less than the old prototype. The reason that this prototype is still bulky is due to the large power supply. As we continue to decrease the size of the power supply, we will also continue to reduce the size of the entire package itself. In this slide, I am demonstrating the capability of the new prototype. As stated earlier, the light guide panels we are using are not correctly etched, and the etching of the light guide is also somewhat in the prototype phase. It's not the amount of light that is being produced by the second prototype that is creating a very dim region on the light guide. It is the light guide itself that is very dim. This is the current state that the project is in. In this video, I am using the newest prototype to drive this light guide. As you can see, the pattern on this light guide is much brighter and has a different etching process. The color detection is also shown in this video. You can clearly see the colors change as I move different colors above the optic. The current test proves that the process to etch the pattern was at fault, and the light guides themselves are not faulty. We plan to eventually reproduce the color and intensity shown in this video through a much larger light guide. Our next goal is to reproduce this color across a 12 by 12 inch light guide panel, and we plan to do that by the end of this year if everything goes well.